All right, so welcome to the first lecture of BIOE 3310, Fluids and Transport for Bioengineers. So I'm just going to start off with a quick outline of today's topics. So first we're going to start off with, if we're sort of looking at a big picture version of this course, so this course, for the first roughly 60%, we're going to be talking about just fluids. And then for the last, say, 40%, we're going to be talking about heat transfer and it turns out that some parts of heat transfer actually use either fluids directly, if you're talking about fluids transporting, cooling things off or heating things up, or various methods that we use to solve heat transfer problems are the same methods that we'll use to solve fluids problems. So this course in general, we're starting off talking about fluids. We're also going to talk about heat transfer. So there we have it. And if you think about it, well, if the first 60% of this course is talking about fluids, perhaps one of the best topics that we could do to start off with is to start off with a definition. Start off with a definition of what is a fluid. And oftentimes if we're thinking about fluids, it's not just like, oh, there's some fluid here. We're interested in how fluids move and what makes fluids move. So if you're thinking back to maybe biomechanics or a mechanics course that you took, we talked about things moving around. We talked about things like velocity and accelerations. So what was responsible for velocities and accelerations? We talked about forces. In the context of fluids, we're often sometimes concerned with forces, but we're often concerned with sort of forces per unit area. So we're going to talk about shear stress, which is basically what causes fluids to move in some cases. So we're going to say, what is shear stress? We're going to give ourselves a more formal definition of that, which is a little bit of a recap from biomechanics, but so be it. So what is shear stress? And if we think about movements of fluids, it's going to actually be important to also talk about shear strain. And for fluids, there's a relationship between shear stress and shear strain. Well, for solids, there's a relationship between shear stress and shear strain. For fluids, there's a relationship between shear stress and shear strain rate. So basically, how quickly is that fluid being strained and what is the stress? So we'll talk about shear strain and then we'll talk about shear strain rate as it relates to shear stress. Then we're going to take a quick detour and we're going to talk about, we're going to do a little side topic. We're going to take a detour and we're going to talk about units, like, meters and seconds and newtons and all that stuff, and dimensional homogeneity. Which is this idea that you can't add something that has, let's say, units of meters to something that have units of seconds and make them sense, or you can't equate something that has units of meters to units of seconds and have it make sense. So this idea of dimensional homogeneity will show up all the time in fluid mechanics, because we're going to have a whole lot of different stuff. We're going to have densities and shear stresses and viscosities and velocity gradients. We're going to have a whole bunch of stuff, a whole bunch of different things that all have different units in this course. And dimensional homogeneity is going to help us keep all of that straight. Then, I sort of hinted at this earlier. For fluids, we're going to talk about shear stress a lot, and we're going to talk about shear strain rate a lot. And I said, hey, these things are going to be related to one another for fluids, and the relationship that we'll use to relate certain things like stresses and strain rates is what's known as a constitutive relationship. So it's basically saying, hey, there's some property of the fluids that relates shear stress and shear strain rate. And in particular, for a lot of fluids that we'll be talking about and modeling in this course, One of the best and most useful and also simplest models is that of Newtonian fluids. So we're going to talk about a shear stress, shear strain rate relationship for fluids, and we'll talk about Newtonian fluids. Spoiler alert, the next lecture is going to be a discussion of non-Newtonian fluids, which I think everyone's heard about to some extent before, and we'll have some cool demos there. Then we're going to talk about the Reynolds number, which makes use of viscosity, which is an important parameter in non-Newtonian fluids. And then finally, we're going to wrap up today's lecture with the discussion of the velocity gradient. Which is related to the shear strain rate. So let's get started. Let's talk about our definition. What is a fluid? So if we're talking about fluids, we'll start with our definition, right? It's always good to start with a definition. And the definition of a fluid that we'll use in the context of this course is a continuum material that cannot support shear stress without continuous deformation. So a continuum material that can't it's a continuum material that can't support shear stress without continuous deformation. So what do we mean by a continuum material? Well, if we think about it, if you zoom all the way in, if I showed you a glass of water, it looks like that material is continuous, right? There's not like weird gaps in the water or bubbles, or there's not like a void in between two chunks of water. But if you zoomed all the way in, all the way down into that water, you would find that water is actually made up of H2O molecules that are discrete and separate from one another. There's space in between them. So if you zoom all the way down to the atomic level, nothing is really a continuum. But if you zoom out a little bit, right, we're not analyzing things at the atomic level in the context of this course. If you zoom out a little bit, then water appears to be continuous, right? We don't, in our everyday lives, we don't notice the weird gaps between individual atoms of water. So that's what we mean by a continuum or a continuous material. And then this idea that we can't support shear stress without continuous deformation. So if I think about water, if I had water and I, let's say, had two plates and I put some water between those plates and applied some shear stress, that shear stress would just keep that water moving. Water, liquids, if I have some container and I, pour that container, eventually that water will pour out of that container, right? So the water itself can't support shear stress unless there's kind of something else to hold that water back, right? And we think about this in contrast to solids. If I have this marker here and I apply some force to the tip of this marker, okay, the marker deforms a little bit at the beginning, but eventually that marker stops, and that marker prevents the solid material of this marker prevents this marker from sort of bending and twisting and keeping deforming and deforming. Whereas if I had a marker made of water and I applied some force, eventually that, the material that made up that marker would just keep going and going and going. So that's what we mean by continuous deformation. Does it keep going and going and going if you apply some shear stress to it? So fluids keep going and going and going. Solids, in contrast, don't. All right, so now what I'm gonna introduce what I'll call a pause and ponder question. So pause and ponder, and I'm going to use purple for sort of all of these pause and ponder questions. And, I know it's a video, you could just keep watching and get the answer, but I want you to actually pause and actually ponder. You're going to get the most out of this course if you actually pause and actually ponder during these pause and ponder questions. So here's a pause and ponder question. The first pause and ponder question is air a fluid? So pause, ponder, work out the answer in your notes, or work out a guess for the answer in your notes, and then I'll reveal the truth. All right, so hopefully you've paused and pondered, and the answer is yes. Usually, almost always, air is actually a fluid. So I know if you talked about fluids, mostly the first thing that comes to people's mind is liquids, like water. But it turns out that air actually is a fluid as well, right? If we think about it, air is a material, right? And although if you zoomed way in on those air molecules, there are individual air molecules bouncing around. If we zoom out, we don't notice the fact that air is made up of individual molecules in our everyday lives. And it turns out that air is very well modeled by almost in exactly the same way and with exactly the same physics that you model water flow or other liquids. So even though air is a gas, yes, it's very well modeled as a fluid in the context of this course, because we don't notice that it's not a continuum. And if we think about it, if I had some blob of air, air has mass and all that stuff, and I applied some forces, some shear stresses to that air would deform continuously. So indeed, air is a fluid. Here's another pause and ponder question. Is sand a fluid? So pause, ponder, work out the result. All right, so hopefully you've paused and pondered, and the answer is usually no. And why might sand not be a fluid? Well, the idea that sand is not a fluid comes from this idea of continuous deformation. So if I had some sand in my hand and I sheared that sand, I applied some forces to it to try to get it to move, that sand can actually resist a bit of deformation, a little bit of shear stress before it starts forming, right? This is how we can form sandcastles. You go to the beach, you make a sandcastle. If sand were a fluid, its own weight would be applying the shear stress that would cause it to deform, right? So sand, in fact, is usually not well modeled as a fluid because under some circumstances it can resist its own, it can resist continuous deformation. It can resist its own weight. Otherwise, we wouldn't be able to make sandcastles at the beach. So sand is usually not a fluid unless it's somehow involved in a landslide or an avalanche, and under those circumstances, you actually might be able to model it as a fluid, but usually not, although sometimes it's context dependent. So, thus concludes our discussion of this definition of, we've now successfully defined what a fluid is. Now let's move on to a discussion of what shear stress is. Now I know I sort of worked shear stress into this definition here. I think we all have at least a qualitative idea of what shear stress is, but let's define this a little bit more quantitatively. Again, we're engineers, and we like quantitative definitions of things. So let's sort of more formally, more algebraically define what shear stress is. So let's look at shear stress. And we'll define it. So if I think about shear stress, there are a couple of things that are important in shear stress, right? So shear stress is basically the force-like quantity that makes stuff shear or sort of move parallel. And if I think about forces being applied to surfaces, if I think about forces being applied to surfaces, I'm going to need to think of a couple of things, right? I'm going to need a couple of quantities to sort of fully define all of the important parts of this shear stress. So to fully define forces being applied to surfaces, I'm going to need three pieces of information. One is I'm going to need the direction of the force. The second thing I'm going to need is a a direction or something that defines the orientation of the surface. And then the third thing, the third piece of information I'm going to need is to define this magnitude. The magnitude of the shear stress, right? So if I'm thinking about the direction of the force, let's say I have some surface right here. I could have forces that are applied in any number of directions, right? I could apply some force like that to the surface. I could apply some force like that, or like that, or like that, or like that, right? I could apply a force in any number of directions. And each of these forces in different directions would definitely result in a different nature of that shear stress and a different behavior of what's going on, what response that surface would have to the shear stress. Another thing that's important is the orientation of the surface, right? If I have some surface like this, or a surface like this, or a flat surface like this, what the orientation that surface makes is important. Do I have, if I imagined, okay, I'm applying a force straight up, here the force straight up kind of makes an angle with the surface, whereas here it's kind of making a right angle, So the orientation of the surface is important for the response that the surface has to that applied force, right? So it's not just the direction of the force that's important, it's the direction of the surface or the orientation of the surface that's important, that matters as well. And then the final thing that's important is the magnitude. So for example, if I had two surfaces here and I were applying, a force like this to one surface and then a little force like this to the other surface, even if the directions of the force are the same and the orientation of the surface is the same for both of these cases, the magnitudes might be different, so the response of the material underneath is going to be different as well. Right? So all of these three factors are important in sort of very rigorously and algebraically defining what this shear stress is. All right, so let's talk about solids, shear stress in solids a little bit. So we're going to talk about shear stress in solids for a little bit. So imagine I had some chunk of solid material. All right, let's just a chunk of solid material here. And if we think about shear stress arises when the force is applied parallel to the surface, right? So if I have some direction of the force and some orientation of the surface, shear stress is, we think about shear stress as the part of stress that is the case when we have some force applied parallel to the surface, right? So shear stress is when shear stress is parallel to the surface, or in this case, perpendicular to the normal of the surface. Right, so when we think about normals, right, we think about a perpendicular to the surface. If we have a force that's perpendicular to the perpendicular, then it's parallel. There we are, right? So if we think about shear stress in solids, let's say I applied some force to the solid like this, what would happen? Let's say I had some chunk of here, and let's say I applied a force like this, what would happen? Well, you could pause and ponder if you want, but I'll just kind of cut to the chase here. If we applied a force like this, well, what would happen? Well, if we dust off our mechanics notes, well, if I apply a force to an object, that object's going to accelerate. So it accelerates unless equal and opposite force is also applied, right? So if I applied a force like this object would shoot off to the right. It would accelerate off to the right. So if we think about forces like this, almost always in the context of solids, and for this course, fluids, we're going to be talking not about cases where we have unbalanced forces like this, but we're going to talk about shear stress where we have some amount of shear stress on the top and some amount of shear stress on the bottom, and these and we're almost always in the context of this course going to be talking about cases where these are equal and opposite, where there's equal and opposites, right? So in this case, we have balanced forces. This object isn't going to accelerate, but what's going to happen to it? Well, if I apply some force to the top of it this way and some force to the bottom of it this way, if I'm talking about solids, right? If I'm talking about solids right here and apply some force to the top and some force to the bottom, I'm now applying shear stress to this object, and the object is going to deform, right? So it's going to deform, right? And the top is going to scoot over to the right, and the bottom is like the bottom would scoot to the left, or if I sort of kept my reference frame and the bottom the same, then the top is going to scoot off to the right. And this deformation is what we call shear strain. Right? And in the case of solids, if you apply some shear stress, you get some shear strain, and that's the end of it. And one way we quantify the shear strain is with this angle. And sometimes the angle that people use is Greek letter gamma. So that's basically a letter people might use to sort of define the magnitude of this shear stress, right? So, and for solids, this shear stress gamma is the shear strain gamma is proportional to the shear stress, and oftentimes people use the Greek letter tau for shear stress, right? So let's say I applied some shear stress tau. This gamma would be proportional to tau. And we'll get into that a little bit later when we talk about constitutive relationships. All right, so here's shear stress. But we need a little bit of a word on shear stress, right? We have shear stress. We oftentimes use the letter tau to define it. And there's sort of this information here. There's a magnitude, there's a direction of the force, and a direction of the surface. So we kind of need all of this information when we're properly defining tau. So let's hash this out a little bit. So a word on convention. A word on conventions for tau. So oftentimes we use two subscripts. We use two subscripts for tau. So let's say we have tau, and this tau is what we'll call the shear stress. There are two important subscripts that will give it, and I'll sort of exaggerate them down here. But the first subscript, it defines a direction. The first subscript defines a direction normal to our surface, right? So if we go back to this, the first subscript is actually this second piece of information here, and then the second subscript helps us define the direction of applied our applied force. So there we have it, right? So the first subscript is a direction normal to the surface. The second subscript is a direction of our applied force. And I'll show a little bit in just a minute. What exactly we might put in these subscripts to help define those things. It turns out, unfortunately, just this information alone isn't quite enough. We need sort of a convention to help us determine sort of what is a positive, in terms of directions of these things. So we need a convention for positive shear stress, and unfortunately we're sort of stuck with two separate conventions that different groups of people use. Frustrating, but here we have it. So for people who work with solids, and oftentimes these are mechanical engineers, and some people who work on fluids. Right, so people who work with solids, oftentimes mechanical engineers, and some people who work with fluids. The positive convention for shear stress is if I had a chunk of material right here, and let's say I had x and y axes like this, positive shear stress would be like this, is sort of is defined to be this way, right? So in this case we have tau, and I'd want to give this tau two subscripts. One is a direction normal to the surface, right? So if I'm talking about this surface right here, the direction normal to the surface is this direction. So the first subscript is going to be y for this tau. And then if I think about, okay, what is the direction of the applied force? If the applied force is going in the x direction right here, the second subscript would be x, right? So mechanical engineers would say, okay, this right here, this situation where I have something pointing to the right on the top part of the surface and to the left on the bottom part of the surface, this is what we're going to call positive tau. So here we are with the other cohort of people. Oftentimes chemical engineers and some fluid mechanicians, and some bioengineers use the opposite convention. I know, frustrating, right? Why can't everyone agree? Why can't everyone agree? Well, this is the world we live in, unfortunately. So the opposite convention that some chemical engineers, some fluid mechanicians, and some BIOEs use is, we still have our y and our x axes. And the convention for these folks is to have positive shear stress pointing in the other direction. So it's still tau y x. So it's still tau yx in the sense that the order of these two subscripts is the same, but chemical engineers have all agreed that positive shear stress does this, and mechanical engineers all agree that positive shear stress does this. But they can't agree with each other on what positive shear stress means. And the result is sometimes people end up with negative signs when they shouldn't have. But in the context of this course, we'll try to stick with one definition. We'll use the same definition for the whole course, and we'll use the same definition that our textbook uses, and that's going to be this one. So even though this definition of what positive shear stress means is different from probably what you used in your solid mechanics class, this is what we're going to use for this class. So I'm sorry to switch things up, but I want to be consistent with the textbook, and the textbook that we have, is other than using the wacky convention, is otherwise pretty good. So here we have it. This is what we mean with positive shear stress. So positive shear stress points the top of the surface this way, the bottom of the surface this way. The first subscript indicates a direction normal to the surface, and the second indicates what direction the applied force is in, and in this case the direction of the applied force is sort of in the opposite x of the x direction by definition for chemical engineers, fluid mechanicians, some BIOEs, including us for this class. Okay, so we talked a little bit. So we talked a little bit about what is shear stress. We also talked a little bit about what is shear strain, right? Shear strain is essentially the angle that if I, had a cube like this and applied some shear stress, shear strain is essentially like the angle that formed here. But it turns out that for fluids, shear strain is not particularly important, but oftentimes it's shear strain rate that is the important thing. So essentially the time rate of change of shear strain. So let's work out what I mean a little more precisely by this shear strain rate. So if I think about shear strain rates, it's the time rate of change of shear strain. So shear strain rate is the time rate of change of shear strain, right? So what does this mean, right? If it's basically, if I have some amount of shear strain, I had some chunk of material. Let's say this is at time equals 0. If I had it, at some later time, it will have deformed to some, it will have deformed by some angle gamma. And if I have a constant, let's say I have a constant shear strain rate, if I wait even longer, it will have deformed even more, right? So now, if I wait even much longer, I have a much larger shear strain. So if I looked at, hey, what is the time rate of change of shear strain? The time rate of change of shear strain, if we think about calculus, would sort of be the time derivative of shear strain, right? So if here's shear strain rate would be its time derivative. So there we have it here, right? It's basically, if I took the derivative of this with respect to time, then it's the rate that's happening, right? So if I had some chunk of material, and let's say I had some non-zero shear strain rate, after some amount of time it would have some amount of shear strain, and then if I waited longer, then it would have more strain that is accumulated. In a sense, shear strain is the integral of shear strain rate, or shear strain rate is the derivative of shear strain. And just as one last little addendum to the convention, a lot of times under some contexts, people signify a time derivative with a little dot over it. So in this case, the little dot signifies a derivative with respect to time, right? So if you see gamma dot, your brain should immediately go, oh, I'm just replacing this with d gamma dt, and d gamma dt is the time rate of change of gamma, right? So in this case, if I have a d gamma dt, after some amount of time, some amount of gamma has accumulated, and then after a longer amount of time, more gamma has accumulated. All right, so let's go back to our outline. We've talked about what a fluid is. Then we talked about, a fluid in a sense that it's something that deforms continuously as long as shear stress is applied to it. And then we sort of hashed out a little bit more of a more rigorous definition of what shear stress was. And we also talked about, hey, well, shear stress results in shear strain for solids and results in a shear strain rate for fluids. So we talked about shear stress, we talked about shear strain, and we talked about that. So there we have it. Now, I sort of drew a lot of diagrams and stuff like this, but I oftentimes think it's helpful to sort of see a visual with a live demo. So prepare yourselves for a live demo. All right, so what do we have for this live demo? I am going to create some shear strain and a shear strain rate in a fluid. So what do I have? I have some honey, and I'm going to put some honey between these two plates, right? So I have one plate down here, and I have another plate up here, and then just another plate so I don't get my desk all messy. And I'm going to put some fluid between these two plates, in this case honey. I'm going to put some honey between these two plates, and then I'm going to draw a little vertical line of food dye so you can sort of track where the fluid particles go. Right, so here we have a little vertical line. Now, so I have this little blob of fluid, and I'm going to apply some shear stress. So if I apply some shear stress, what happens? Well, if you notice, we get some shear strain, right? We see this blob of dye now makes an angle, and as soon as I stop applying that shear stress, the shear strain stops happening, right? And if I apply shear stress in the other direction, then it kind of goes back to where it was before, right? So if I apply some shear stress, then I get some shear strain, and as soon as I stop applying that shear stress, I stop getting that shear strain. So, this demo with honey is supposed to kind of recapitulate this picture that I'm talking about here, where when I'm applying some shear stress, then I get some shear strain. Right? So my hands were essentially applying some through the two cutting boards that I had on the top and bottom, we're applying some shear stress that resulted in a shear strain rate, and that shear strain rate was kind of signified by the angle that the little blob of blue food dye was making. That blue food dye was, that angle that blue food dye was making was kind of rotating as that fluid was being sheared by the shear stress that I applied. So there was, while I was applying that shear stress, there was a non-zero shear strain rate. Okay, so there we have it. Shear stress, shear strain, and for fluids, when I apply shear stress, I get a non-zero shear strain rate while I'm applying that shear stress. Okay, so there we have it. Now, let's take a little bit of a side topic into units and dimensional homogeneity. So if I think about anything that occurs in real life, right? Any sort of real physics is if what do we mean by units, right? So physical quantities have units, right? So for example, if I wanted to tell you how long, right? If I wanted to tell you how long this marker was, right, I'd be talking about its length, and almost always in the context of this course, I'm going to be talking about SI units, right? I don't want to confuse people with two separate unit systems, right? So physical quantities have units, and grown-ups use SI units. And if we think about length, the SI units of length would be meters, right? If I think about area, well, the area of this sheet of paper I would get by multiplying the lengths of the two sides. So units of area would have meters squared, right? If I think about things like shear stress has units of, is essentially a force per unit area, right? If you dust off your biomechanics notes, right, the shear stress is the force divided by the area, right? So units of shear stress is force per area. So if I think about what SI units, it might be newtons per meter squared, which is given a special name of a Pascal. But you could also work out Newton as a kilogram meter per second squared. So a Newton per meter squared would be a kilogram meter per second squared per meter squared. Or you could do a little bit of cancellation to cancel out these meters and one of the meters in the denominator. So usually people don't use kilograms per second squared meter because that's kind of what even is that? Right? But people oftentimes think about shear stress as a force per area or a Newton per meter squared. All right, so physical quantities have units, right? And these units, in the context of this course, we'll be talking about SI units all the time. If I think about dimensional homogeneity, right? So what is the relationship, how do units play into dimensional homogeneity? Right, so if I think about dimensional homogeneity, this is basically saying, hey, if you set two things equal to one another, right? So if you set two things equal or add two things, if you set two things equal or add two things together, they must have the same dimensions or the same units. Right? It doesn't make sense to add a length to an area or a shear stress to a length. It doesn't make sense to set something with units of length equal to something of units of area, right? I can't say that this marker is just as long as the area of this cutting board. Like, what? That doesn't even make sense, right? So this idea of dimensional homogeneity is just that. It's saying, hey, you can't add two things that have separate units. You can't equate two things that have separate units. And it turns out that this is actually going to be super helpful to us for doing some sanity checks and solving some problems in fluid mechanics. All right, so this idea of dimensional homogeneity will oftentimes help us work out relationships between things. So, side topic units, dimensional homogeneity. This ties in very closely to constitutive relationships. So now we've set the stage. We've talked about shear stress, we've talked about shear strain and shear strain rate, we've talked about dimensional homogeneity. So now let's talk about constitutive relationships, which kind of brings all of this together and basically allows us to relate shear stress to shear strain or shear stress to shear strain rate in a algebraic way where all the units work out due to dimensional homogeneity. So let's proceed. And it turns out we're going to have different relationships. I'll talk about it for solids, and I'll also talk about it for fluids. And we'll sort of make comparisons and contrasts between those two. So we'll talk about constitutive relationships, or there we have it. So if we think about solids, let's talk about solids first, since we have the most experience and the most intuitions with those. For solids, there's a relationship between shear stress and shear strain. And, if we think about this for solids, this is maybe most apparent with like normal stress and normal strain. But if I have some, let's say, rubber band, right, and I apply some force, apply some stress to it, the more force I apply, the more strain I get, right? And then if I let go of that force, ouch! If I let go of that force, that strain goes away, right? So in this case, when there's a lot of stress, there is a lot of strain for solids. And when there's no stress, then that strain goes away, right? So if I apply stress, I get strain. If I apply more stress, I get more strain. And then if I let go, there's less strain, right? So in this case, shear stress is proportional to shear strain for solids, right? And, okay, so let's start working out an equation for that, right? If I think about shear stress, I might call this tau, right? Let's not worry about subscripts for now. Let's just say, sort of generally shear stress. If I think about shear stress being proportional to shear strain, right? Shear strain, of course, being this quantity gamma that we talked about earlier. Well, anytime I know one thing is proportional to another thing, I can make that proportionality something equal if I include a proportionality constant, right, between it, right? So shear stress, I can say, is equal to shear strain if I multiply shear strain by some appropriate quantity. That's the scaling factor that scales the shear stress to the shear strain. And for solids, I would call this quantity G. And just because of like sign conventions and all that stuff, let's just sort of be Sith and work in absolutes, right? So we're working in absolutes here. We're just saying, you know, the magnitude of shear stress is proportional to the magnitude of shear strain times this quantity here, right? And for solids, we call this the shear, which is related to but not exactly the same as Young's modulus, right? If you're talking about normal stress and normal strain, right? So in this case, if I have some solid and I have a little bit of shear stress, I get a little bit of shear strain. If I apply more shear stress, then I get more shear strain, and the relationship between them is this shear modulus. So prepare yourselves for a pause and ponder question. Pause and ponder. Pause and ponder, what are the units of G, right? And in order to help work this out, it might help to remember, you know, what are the units of shear stress, also the units of shear strain. I talked about this as an angle, and almost always people talk about this angle in terms of radians, but remember, radians secretly aren't actually units. So radians actually secretly don't have units. Radians secretly don't have units. So consider that when you're pausing and pondering. What are the units of shear modulus? Okay, hopefully you've paused and pondered. Well, if we think about it, shear stress, angle in radians, if I want to work out what all of this is, well, I know shear stress has to have units of newtons per meter squared, or pascals, right? You know, they're essentially the same thing, right? If I know this has no units, then what must the units of G be? Well, by dimensional homogeneity, right? By dimensional homogeneity, saying that if the left-hand side of everything on the left-hand side has to be equal to everything on the right-hand side in terms of units, then shear modulus needs to have whatever units to make those both work out. So in this case, shear modulus has to have units of, well, if there are no units for here, then shear modulus has to have units of newtons per meter squared. There we go. So this relationship right here is the constitutive relationship for solids, and it's not the only constitutive relationship that exists, but it's the for solids, but it's the constitutive relationship for what we call linear elastic or Hookean for Hookean solids, right? So this is essentially like the simplest and probably the most widely used and the most useful relationship, constitutive relationship that relates shear stress to shear strain for solids. Now, it turns out there's a similar-ish but slightly different rule for fluids. And of course, there are many constitutive relationships for fluids, but one of the most useful constitutive relationships for fluids is that of Newtonian fluids. So we've talked about in general what constitutive relationships are, right? They're relationships between shear stress and shear strain, or shear stress and shear strain rate. And we talked about a constitutive relationship for Hookean solids. Now let's talk about a constitutive relationship for fluids, the most useful and common and simplest of which is going to be that for Newtonian fluids. So let's work it out. So here's a constitutive relationship for Newtonian. Here's a constitutive relationship for fluids. It's not the only one, and it's not necessarily the right one for all fluids, but it's certainly the simplest and easiest and the most useful which is going to be Newtonian fluids. And we'll talk about non-Newtonian fluids in our next lecture. But for Newtonian fluids, we have shear stress. We still have shear stress on the left-hand side. And for fluids, its shear stress is proportional to, not proportional to shear strain, but proportional to shear strain rate, right? So in this case, we have shear stress being proportional to shear strain rate. So for solids, shear stress was proportional to how much you've stretched out that solid or deformed that solid. So for solids, it's essentially how much stress is proportional to how much it's stretched or deformed. Right? Stress is proportional to how much it's deformed. For fluids, stress is proportional to how fast you're deforming. How fast you're deforming the fluids. But it's not just shear stress is equal to shear strain rate. We need to include this idea of a proportionality constant between the two. Right? So for solids, this proportionality constant was the shear modulus, and the shear modulus is a material property. A material property, right? So rubber bands have one shear modulus, but marker has a different modulus, and steel has yet a different shear modulus. So in this way, this proportionality constant, this shear modulus, is a material property that makes one solid behave differently from other solids. For fluids, the constitutive relationship that relates shear stress to shear strain rate is also a material property, and it's called the viscosity, right? So we need our proportionality constant, and it's called the viscosity. Right? So you might have heard of viscous fluids or like the fluids that are very viscous, fluids that are less viscous, right? We talked about honey. Honey is pretty high in terms of viscosity, right? It's pretty thick, it's pretty oozy, right? Whereas water is less viscous and air is still less viscous, right? So we have honey on one side, air on the other, water somewhere in the middle, right? So different materials have different relationships between shear stress and shear strain rate, and what makes one material different from the other is its viscosity. We give viscosity a special name, a special variable, and I'll call it Greek letter eta. So this is Greek letter eta, and there we have it. And we need to, now's a time where we can be a little bit careful with our signs, right? If shear stress is sort of defined, if we're using the definition of positive shear stress, where positive shear stress points this way, but we're also using the definition of shear strain, being an angle that's defined clockwise, then actually it's negative shear stress that results in a positive shear strain rate, right? So we actually need to include a negative sign in this definition, right? Because positive shear stress is defined to kind of point like this, whereas positive shear strain is kind of positive shear strain rate would sort of be the speed at which it's rotating clockwise, right? And of course, and positive shear stress would result in negative shear strain, right? Because if you shear something this way, it's going to be, if you apply forces like this, then it's going to rotate in a negative direction. Or if we have, or vice versa, right? So that's why we have this negative sign here to basically account for our somewhat weird definition of shear stress that we have to use because, well, you know, you got to pick one. Okay, so viscosity is this proportionality constant, and fluids with a higher viscosity, like honey, basically saying for a certain strain rate, if the viscosity is really high, it means you're going to need to apply more shear stress to account for that amount of shear strain rate. So for honey, where there's a very high viscosity, we need a lot of shear stress to support even a moderate shear rate. Whereas something like water or air that has a very low viscosity, we need very little shear stress to scale up to that or to scale that shear strain rate up. All right, so prepare yourselves for a pause and ponder question. What are the units of viscosity? What are the units of eta, of Greek letter eta? So pause, ponder, consider, and you know, let's see how it compares to the result. Okay, so hopefully if you paused and pondered, let's work out the results. If we think about shear stress, right? Shear stress has to have units of newtons per meter squared, right? Regardless of whether it's shear stress on a solid or shear stress on a fluid. If I think about shear strain rate, right? This shear strain rate, that's equal to d gamma dt. And if I think about d gamma dt, well, gamma doesn't have any units, but if I differentiate something with respect to time, then I end up with seconds in the denominator, right? So if I think about, you know, if I think about dx dt, right? If I think about x would have units of meters. If I think about dx dt, that's equal to velocity, and velocity has units of meters per second, right? So when you differentiate something, sorry, x has units of meters, dx dt is velocity, which should have units of meters per second, right? So when you differentiate something with respect to time, you end up with seconds in the denominator. So what does that mean? Shear strain rate has to have units of 1 over seconds. So if shear stress has units of newtons per meter squared or pascals, shear strain rate has units of 1 over seconds, then that means viscosity, or Greek letter eta, has to have units of Pascal seconds, right? So Pascal times seconds multiplied by 1 over seconds gives us pascals, or Newton per meter squared seconds, or if you broke newtons into its kilograms per meter second units, then Newton seconds per meter squared is the same as kilograms per meter second. So in this case, viscosity has units of Pascal seconds or kilograms per meter second. All right, so let's just add one quick thing to this viscosity here. Viscosity might be, you know, we could have two cases for viscosity. One, is it a constant? And the other is it not a constant? And if velocity is a constant, then we call it a Newtonian fluid. And if it's a constant, oftentimes instead of giving it this Greek letter eta, if it's a constant, sometimes we give it the Greek letter mu. We give it the Greek letter mu instead, right? So if it's a constant, we oftentimes use mu instead of eta to kind of give it that extra signification that, like, yes, this is a constant instead of something that could depend on, you know, strain rate or something else in our system, right? So if it's a constant, we give it Greek letter mu instead of eta in this spot here, and we call it a Newtonian fluid. Right, so Newtonian fluids are constant viscosity. But if viscosity is somehow variable in some way, we'd end up with what's called a non-Newtonian fluid that we'll talk about next time. Right? So if it's constant, then we have we'll give it the letter mu instead of eta in this relationship. So there we have it. we've talked about constitutive relationships, right? So, and we've talked about the most important constitutive relationship for fluids, which is this Newtonian relationship, where we have shear stress proportional to shear strain rate, and the proportionality constant is mu for Newtonian fluids. Let's now talk about one of the cool ways in which mu appears and sort of broadly characterizes flows. Again, this is a little bit of a side topic, but you can't get too far in fluids without talking about the Reynolds number. All right, so let's talk about the Reynolds number, which is this cool example that sort of involves both dimensional homogeneity as well as viscosity. So it kind of ties it together. So Reynolds number is this super useful number in the context of fluid mechanics. It's given R sub E, and it's defined as a ratio of a couple of quantities. So in the numerator is rho, Greek letter rho. I know it looks like a P, but there's a little difference in the tail here. So it's Greek letter rho, and it signifies the mass density of the fluid. And of course, mass density would have units of kilograms per meter cubed. Although, in high school chemistry, it would still be a mass per volume if you expressed it as grams per milliliter. The second term in the Reynolds number is a velocity. So let's talk about a particular case where there might exist some Reynolds number for some system. So let's imagine we have a sphere that's traveling through some fluid with some velocity, right? So we have some sphere, and it's moving with some velocity v through the fluid. All right. So that sphere might have some velocity. And of course, velocity would have units of meters per second. And then the final thing in the numerator of the Reynolds number is d, which is typically some characteristic length scale. So for example, for a sphere going through a fluid, the relevant length scale might be the diameter. So this is some important length scale. For example, diameter. And of course, diameter would have units of length in SI, which could be meters. And then in the denominator of the Reynolds number is the viscosity of the fluid. So Reynolds number, of course, would make the most sense for Newtonian fluids where viscosity is some kind of constant, right? So here we have the Reynolds number and the viscosity of the fluid. And if you go back in your notes, viscosity has units of kilograms per meter second. All right, so we have the Reynolds number. Prepare yourselves. Mass density and viscosity would be properties of the fluid around this sphere, and the velocity would sort of be related to its state, right, how fast it's moving, and then the length scale, the diameter, would be a property of the sphere, right? So Reynolds numbers are kind of properties of systems, right, where it's sort of involves both the fluid and the system and some objects in the system and how those things are moving. So Reynolds number is kind of a property of the whole system. So prepare yourselves for a pause and ponder question. So pause and ponder. What are the units of Reynolds number? So take a moment, pause, work it out yourself. Okay, so hopefully you've paused it and worked it out. Let's work out what the units of Reynolds number are. So if we plug in kilograms per meter cubed and meters per second and meters, and then in the denominator we do kilograms per meter second, then we can see, all right, which of these are going to cancel out? Well, kilograms would cancel with kilograms in both the numerator and denominator. 1 over seconds in the numerator would cancel with 1 over seconds in the denominator. And then if we looked at this, meters times meters over meters cubed, all of these together are kind of like 1 over meters, and then there's of course a 1 over meters in the denominator here, so those cancel out as well. So hey, wait a second, if we look at all this stuff, the answer to this pause and ponder question is it's what's called a dimensionless number, in that it doesn't have units, right? So if it's a dimensionless number, it doesn't have units. It turns out these dimensionless numbers come up all the time in fluid mechanics, and in physics and engineering as well, but particularly fluid mechanics. So the Reynolds number kind of allows us to sort of put things in a ratio and kind of broadly characterize flows. And it turns out that some flows are similar. For example, let's say I had a flow where the velocity was twice as fast, but the diameter was half as big. Those two flows would still have the same Reynolds number. And it turns out some characteristics of the flows, even though they have some differences in the details, if the Reynolds number is the same, a lot of times some characteristics of the flow is the same. So let's go back to this example where we have some sphere moving through some fluid at some velocity, and kind of look at two cases, two sort of extremes for what the where we might observe differences in the flows depending on differences in Reynolds number. So let's imagine case 1 where we have a bacterial cell settling in water, right? So I have some bacterial cell, it's moving through the water at some velocity. Bacterial cells can sort of very slowly kind of settle through the water. And then another case where we have a skydiver in air, and of course skydivers are a lot bigger and they're also going to be moving a lot faster. So if we think about a bacterial cell in water, the velocities of bacteria are going to be pretty slow. The diameters of bacteria are going to be very slow, right, microns. And the viscosity of water is, it's not the most viscous fluid, but it's pretty high, right, especially compared to air, right? So if we think about what the Reynolds number of bacterial cells in water, these are going to have low Reynolds numbers. And it turns out that bacterial cells moving through water at very low Reynolds number, the flow around the bacterium as it's moving through that water is very orderly, right? There's not a lot of swirling, there's not a lot of chaos, right? All that fluid sort of follows very nice, smooth paths, and at low Reynolds number you get what's called laminar flow. So at very low Reynolds numbers we typically get laminar flow, for example, flow around a bacterium as it's moving through water. If you want some more interesting laminar flow examples, check out Smarter Every Day on YouTube. We contrast this to a skydiver in air. Skydivers are probably moving pretty quickly, so they have pretty large velocities, and they probably have, compared to a bacterium, skydivers would have a pretty large diameter. Furthermore, air is a lot less viscous than water, so air's viscosity being much lower and a small number in the denominator would mean sort of that contributes to a larger Reynolds number. And although air has a lower density than water, it turns out these other factors outweigh the density. So skydiver in air is characterized by a high Reynolds number and turbulent flow. So what might flow around a skydiver look like? We might have a whole bunch of kind of swirling vortices trailing in this wake behind the skydiver, and the flow is kind of very chaotic and very sort of messy, very varying in both space and time, compared to sort of this orderly flow around the cell at low Reynolds number. So that's some key differences. So what's the key takeaway? Reynolds number involves viscosity and some other parameters, and if we're careful with all of our units, we notice that Reynolds number is a dimensionless number. Dimensionless numbers will show up, and we care a lot about the dimensions and the units of everything in the context of fluid mechanics. So, thus concludes our discussion of Reynolds number. Now let's move on to velocity gradient. So what do I mean by velocity gradient, and who cares about velocity gradient? So velocity So what is the velocity gradient and who cares about it? So velocity gradient basically describes how rapidly or how strongly flows vary how strongly do flows vary spatially, right? i.e., do we get large changes in velocity over short distances? Do we get large changes in velocity over short distances? And it turns out, why do we care about large changes in velocity over short distances? Well, it turns out that there is this velocity gradient turns out to be almost identical to the shear strain rate. And I'll show you why. Right? So velocity gradients, i.e. flows that have large variations in velocity over short distances, are almost identical to flows that have a high shear strain rate. Why do we care about high shear strain rates? Well, if you remember, for Newtonian fluids, there's a relationship between shear strain rate and shear stress. So what does this mean? We're looking to develop a relationship between velocity gradient and shear stress. And this is going to be a more useful relationship than the sort of relationship between shear strain rate and shear stress. Sort of using velocity gradient is going to be more helpful than using shear strain rate, because shear strain rate, it's like this angle, the rate of change of this angle, like what do you mean is an angle, right? Whereas velocity gradients, this is something that I can measure, this is something that I can observe. So let's make an observation of velocity gradient. All right, so let's look at velocity gradient. So I'm going to bring back my example with the cutting boards and the honey. So here I have two plates, a top plate and a bottom plate, and I'm going to get a little bit of food dye to dye part of the honey, and I'm going to put a blob of honey between these two plates. So here I have these two plates, and I can sort of drag a little line. Let's sort of get this all set up first. So I'm just going to drag a little line of dye, so you can see the fluid, and we're going to observe a velocity gradient in this flow. If I stretch the top, if I move the top plate but hold the bottom one still, so initially this line starts out vertical. And if I move it over like this, we notice the particles closer to the top plate moved faster, moved more than the particles at the bottom of the plate. And that's made evident by the dye sort of staying right next to this original point at the bottom, whereas moving over with the top. Oh, delicious. So if we look at this flow, right, where we had this shearing action of this top moving over, we notice that the particles at the top move faster than the particles at the bottom, so there must be a velocity gradient within this flow, right? So we can say the top moves faster than the bottom, so there's a velocity gradient in this flow. And we also suspect that, I needed to apply some force to move these plates, so there's shear stress associated with this flow as well. So, qualitatively, we might say, hey, okay, there's a velocity gradient when flow varies spatially, i.e. we have faster moving particles at the top compared to the bottom, right? So that's kind of what it is. Who cares? Well, we're looking to develop a relationship between shear stress and velocity gradient, and that's going to be useful to us because when we're trying to characterize and measure and observe and describe flows, velocity is going to be way more useful than this sort of abstract angle idea of shear strain rate. So let's work out what this relationship is going to be. So let's work out this relationship between velocity gradient and shear strain rate. And as we do that, I'm going to ask you to sort of consider to sort of remember the example of the honey with the dye, we'll have two plates moving. Let's just imagine two points within that flow. So I have a point here and a point here. Let's say I sort of have like an x, y coordinate system that kind of describes these points. So I have 2 points. Let's say this point is at position y, and then let's say they're separated by a distance delta y. So then this point is going to be at location y plus delta y. And we can imagine the point up here had a higher velocity than the point down here, right? So the point down here, let's say it's moving, it has some velocity. It has a velocity in the x direction, so I'm going to say it has some velocity. V sub x, with our x indicates that it's a velocity in the x direction, and it's a Vx. This guy up here also has a Vx, but it has a different Vx, a different one from this one. This one has a Vx as well. This Vx is at location y, whereas this Vx is at location y plus delta y. And these two velocities are different from one another. So let's use this idea of these two different velocities to try to get some relationship between shear strain rate and this idea of velocity gradient, i.e. a spatial variation in velocity being related to this shear strain rate. So let's kind of consider the fact that these 2 points are kind of trucking along at their two different velocities. Let's sort of consider what would happen if we let some time, for example, delta t, pass. So if I let some time delta t pass while these things are moving this way, this bottom one, let's say, would cover some distance, and the top one would let's say cover a different distance, where now this top one is, let's say moved all the way over here, where the bottom one only moved this far. The bottom one would move, this one would move a distance, so this covers distance. This one covers a distance. Vx at position y times delta t, right? Distance is equal to velocity times time, so if it's moving at Vx over a time period delta t, that's how much distance this bottom one is covered. Now similarly, this top one is going to cover a distance. This top one is going to cover a different distance, Vx at y plus delta y times delta t. Right, so over the same period of time, they have different distances covered because of their differing velocities. So initially, these 2 points kind of don't have sort of any angle between them, right? They're lined up perfectly vertically, but at some time later, I can imagine that they sort of form a triangle, right? And initially, if there's no angle, and later on there's some angle between them, I might call, this change in angle, let's just call it delta gamma, right? In a sense, that's a shear strain that this chunk of fluid has undergone, right? These 2 points started vertically and ended up tilted sort of like this, so there was some shear strain in the fluid, and it turns out that shear strain angle we can kind of work out geometrically. So let's say there's this angle of this triangle, and that's the shear strain angle right there. Hey, wait a second, can we relate this shear strain angle to some of these velocities? Why, yes, we can, right? If we imagine, we have some angle here, well, the tangent of this angle, I'll call the tangent of delta gamma, is just opposite over adjacent, right? If we dust off our high school trigonometry. So adjacent, well, the adjacent is this delta y, right? We said these 2 points were separated by delta y. So the adjacent is delta y. And the opposite, well, the opposite is the difference between this top leg here and this bottom leg here. So it's going to be Vx at y plus delta y times delta t minus Vx at y times delta t. Right? So we're going to have a difference between those two things. All right, and you can imagine if we look at this situation over here, and we anticipate kind of moving towards, we're moving in a calculus-y direction. Get ready, calculus is coming, calculus is coming. All right, so get ready to move in a calculus-y direction. If you imagine, if I kind of imagine this happening over infinitesimally small timescales, if you dust off your high school trigonometry, for very small angles, tan of something is approximately equal to just the thing itself, as long as you express it in radians, right? Remember, like, sine theta about equals theta for small angles. Well, in this case, tan of delta gamma is approximately equal to delta gamma over small angles. So that's going to be useful. So where is this taking us? Well, this is taking us in a sort of calculus-y direction. So if I look at this top part here, both of these terms in the numerator have delta t, so I could factor out that delta t and then divide both sides of the equation by it. So what would that look like? Now my left-hand side is delta gamma over delta t, and then the right-hand side of the equation is left with, well, I still have delta y in the numerator, but now I just have the difference of those two velocities in the numerator. So how does that help us? So if we imagine over short timescales, and if we're imagining like calculusly small timescales, right? We're moving in a calculus direction here. You know, we can take limits as deltas go to 0. And if we take limits as deltas go to 0, delta gamma over delta t, this finite difference essentially becomes a derivative. So it's a derivative of gamma with respect to time, right? So this left-hand side essentially becomes d gamma dt. And hey, wait a second, d gamma dt we just said was gamma dot. And this is our shear strain rate. Sweet. Okay. We're moving in a good direction here. We were able to pull shear strain rate out of this sort of geometrical reasoning that we did. And then if we think about the right-hand side, well, the right-hand side, if you remember, this is kind of the definition of a derivative. This is the definition of a derivative. If you dust off your high school calculus notes, right, if we have like f of x plus delta x minus f of x over delta x, if you take the limit as delta x goes to 0, then you get a derivative. In this case, it's not f and it's not x, but rather vx and y. So what does this mean? This definition of a derivative essentially basically becomes a derivative of velocity with respect to y, right? So we have a derivative of velocity. So it's a derivative of our x velocity with respect to y. And this basically says how much does x velocity vary with y? And if x velocity varies a lot with y, then there's going to be a derivative, a change in that x velocity with y. And if x velocity varies a lot with y, then that's a case where we have the top plate moving fast and the bottom plate not moving at all. And in that case, we get a large shear strain rate. So what does that mean? Large velocity gradients mean large shear strain rates. And if we bring back our Newtonian fluids, shear stress is proportional to shear strain rate. So what does that mean? If shear stress is proportional to shear strain rate, that means shear stress is also proportional to velocity gradient in the same way. So what does that mean? Well, we can kind of, we can plug it in, and we can basically say tau yx is going to be equal to minus eta, right? We still have that proportionality constant of the viscosity times dvx dy. And there we have it. So now we have a relationship between shear stress and velocity gradient. So the more rapidly flows change in their velocity spatially, right? The more spatial variation there is in the velocities of flows, then the more shear stress is, right? In a sense, if I want to move that flow faster, if I want to have a greater difference in the velocity of my top plate than my bottom plate, I'm gonna need to apply more shear stress, i.e. more force per area, in order to make that happen, in order to sustain that more intense velocity gradient. All right, so let's sort of summarize everything that happened. If we talk about, we first talked about what is the definition of a fluid, and we said a fluid was a substance, a continuum substance that couldn't support shear stress indefinitely without experience deformation. Then we said, hey, well, if we're going to have shear stress in this definition of fluid, we need to talk about what it is. And we use the Greek letter tau to indicate shear stress, and that's a force per unit area. And if we apply shear stress to fluids, then those fluids experience a shear strain rate. If we apply shear stress to solids, they experience just a shear strain. That then got us talking about constitutive relationships, but before we talked about constitutive relationships, we needed to talk about the units and how, if we have units on the left-hand side of the equation or the right-hand side of the equation, those units need to balance up due to dimensional homogeneity. We talked about constitutive relationships between fluids and the most important, and for solids, and the most important of those constitutive relationships relates shear stress to shear strain rate, was that of the Newtonian fluids. We talked about, for Newtonian fluids, the viscosity, i.e. that proportionality constant, that is a property of the material, is constant. It turns out viscosity played into Reynolds number, which we talked about a little bit now, but will show up later. Reynolds number is useful for cool things like characterizing whether flows are laminar or turbulent. Then finally, we talked about the velocity gradient, and we used a sort of geometrical argument, right? We sort of talked about how velocities could vary spatially, and it turns out that velocity gradient was actually the same as shear strain rate, and if velocity gradient is the same as shear strain rate, then we can put our shear stress for fluids in terms of a velocity gradient. So we can put our shear stress for fluids in terms of a velocity gradient. And that's going to be super helpful to us in the next lecture. So with that in mind, I hope you enjoyed this fluid lecture, and good luck with your studies of fluids. Thank you.